You're supposed to approximate area, but it's not a triangle, it's not a trapezoid, it's not a circle, so we're just approximating. We can't do it exactly. So we're going to actually approximate the area of those boxes, and the bottom one we're going to approximate with the table. So there's some like compare and contrast, right, with approximating. But what are the quantities being dealt with? And number one, what does the graph actually show?
Water pumping versus rate.
There's water pumping, but it says that the graph is the graph of rate. What would the units be?
Gallons.
Gallons per hour. Number two, what do they give you? What's that table? Acceleration. And it asks about what quantity? Velocity. Hold on. What's acceleration's relationship to velocity? It's the first derivative. So acceleration is the rate of change of velocity. So they give me a rate in the table. And number one, what are they asking for?
Total gallons.
Okay. So number one, they give you gallons per hour. They're asking about gallons. Number two, they give you, basically it's a way of saying feet per second, or velocity per time, dv/dt. And they're asking you for velocity. And both of them, you have to go backwards. What do I mean by that? You can try to explain what I mean by you have to go backwards.
Use the idea of area.
Use the idea of area, or another way of putting it is use the idea of an integral. Because you've been given a rate, and you need to go back to the original. Remember, derivatives are rates, right? So I can give you position, you can find the rate of position, whether with a slope formula or with a derivative, and you would find velocity, right? Average or instantaneous. You can take the derivative of velocity, or do an average rate of change of velocity and get to either an average or an instantaneous acceleration. Derivatives go forwards like in motion. But then integrals are required if we ever need to go back. So as you look at number 1 and 2, they give you rates of something. Number 1 is the rate of change of the gallons per time. And then the second one is the rate of change of velocity per time. Right? Now look up here at our forever card. Our forever card, which is this one. Guys, this is forever number 43, right? Forever number 43. Forever number 43 says, hey, we can figure out the position, and I want you to actually underline the at. This isn't position over, this is position at. It's not position over. Which wouldn't even be position, it would be change in position over. This is position at. Look at the forever card. The forever card says we can find the position at time b, we can find the position at time b given, who's in the integral? Velocity. If they give us velocity with an integral or with the idea of area, which is a way of approximating, or if it's geometric, finding exactly the integral. We can integrate a rate and we can get back to an original, but pause. Who's the third player? We have what we're trying to find. We have the integral or the area of velocity. But who else is there?
Initial position.
Initial. So the idea is to get the final, if you want to put it in words, to get the final, we need to start with the initial, and we need to add the change. That's basically what's going on. Because as we know, a definite integral, right? A definite integral from a to b of a rate is equal to the antiderivative of b minus the antiderivative of a. If you want to write that in your packet, you can. If you want to write it down here, you can. But the idea is an integral just finds us a change, just finds us in what the displacement was or what the net change was. Now, if we start throwing absolute values in there, we start splitting it up into zeros, that's going to be total distance traveled that we talked about for quite a while back when we did the motion packet. But if we ever need to find the position at, where is it currently at, we need to say, okay, to find what's going on at the end, to find out what the current amount is, we need to start with what we started with, start with the initial amount or the initial position, and add the change which is found from the definite integral as Sean said once again, can also be found with area, whether a trapezoidal sum, whether looking at a graph like number 1. But guys, motion does show up on the AP, not very often. That normal motion like we're used to is on the FOQ. I want you guys to go turn in your packets to the ones with words. I mean, they all have words, but go find the ones that are not multiple choice. Find me the first one. It has like an A, B, and C. Doesn't take long, right? Find the first A, B, and C problem. Okay. What's the scenario? What's the situation? What are we dealing with? Temperature. Okay, is the temperature changing at all?
Yes, because it's weight plus.
So it gives us information about the temperature itself. In A, B, or C, does it ask us to think about the rate at all? Or the derivative at all?
C. The rate.
Okay, good.
Yeah.
So part C starts talking about rates. Now, long story short, this is a problem having to do with temperature and just how cold it is outside, right? And then part C says something about cooling the house down. Okay, turn to the next one. So we could have temperature. It has nothing to do with motion, and yet it could still have rates, and it could still have integrals and derivatives. Number 7, what's going on?
People and part.
We have an amusement park. So instead of degrees Fahrenheit per hour or per day, now we have people per hour probably, right? People going in, people going out. We had people at Magic Mountain recently, Disneyland recently. Okay, it's an amusement park. But, question, could people per hour kind of be like velocity? It's just a rate. We could integrate people per hour. We could take derivatives of people. We could go backwards or forwards as far as with whatever quantities they're dealing with. Whatever, people per hour, it's an amusement park, whatever. Keep going, the next one. So we could have motion with feet per second or miles per hour. We could have degrees Fahrenheit per hour. We could have people per hour. What's this one?
2 runners.
A runner. What? Which is going to be distance, right? But they're now having us, so this is kind of more motion-y in the sense that we probably have actual like distance measurements. Meters. Okay, meters per second. That one's kind of basic motion-y, sort of. Go to the next one. PS, pause. Look at that graph for the runner. Look at the graph for the runner. Can you tell that they might have you find that area? Because it's a super nice one and you don't need a function for it? Next one. Okay, so very motion-y. Particle along the x-axis, very motion-y, but not like normal miles per hour. It's literally like, think of the x-axis as a little dot, and he's moving along it. That's it. As soon as he gets off that x-axis, the calculus gets way more complicated. Not way, but more complicated with parametric equations. Anyway, it's a little point on a line. He's going back and forth. Kind of boring, but motion. Next one. What's the scenario of that?
Oh, the way people turn on Thomasville, Oregon intersection. The rate at which they turn.
Thomasville, Oregon, huh? Kiddos, do you think that Thomasville, Oregon really has anything to do with how we answer that question?
No.
No, not even close, right? But why'd they put that? I don't know, to make it somewhat real-life-ish and to also confuse you.
Because math exams never require you to.
Okay, so we have a turn that's being made, a right-hand turn, a left-hand turn, and I think it has something to do with cars per hour. The ultimate view of what's going on.
Yeah.
How many cars are going through the intersection. Next one. So that degrees Fahrenheit per hour, we've had meters per second, we've had people per hour. What is it?
Sales of concert.
Concert tickets. I think I have that one up here.
Gosh, what concert tickets?
Concert tickets. What's this one going to be? Probably people per hour, right? If we were going to a rate. People per hour. Okay. Next one. Is there a next one?
Yes, rate at which T equals, so temperature again.
Temperature again. Degrees Fahrenheit, degrees Celsius? Is there snow?
Celsius.
Oh, quality! Hey, look at part C! Or part D. There are biscuits! Tea and biscuits? Crumpets and tea?
That's how
I didn't remember what was what. I just remember it was there.
That's my hobby plate.
I see, there are biscuits. Now, kiddos. Guess this year. What year was this?
You're gonna have to know the
2011. This year, the kids didn't like the tea and biscuits problem. Has anybody heard last year about the bananas problem?
What are potatoes?
Oh, there was a potatoes problem
Being
too.
like tossed into like.
The kids didn't like the potato problem,
Stalking a
and they
store.
didn't like the banana problem. The banana problem was like a store associate stocking bananas,
Yeah.
and then and so they were stocking before the store opened, and then the store opened, and people started coming and taking the bananas. It was a problem just like people going into the park and out of the park. It was very similar to biscuits in the oven taken out of the oven. Temperature going up and temperature going down. But guess what they all got tripped up on last year?
The banana.
It was a potato. You should have seen all the memes about that one. It was a potato. They freaked out. I'm like, it doesn't matter. It could be potatoes. It could be bananas. It could be concert people. It could be amusement park people. It could be a pot of tea and biscuits. I don't care what they give you. We're looking at the math behind it. Does that make sense? Does it matter whether it's some poor girl trying to like bike to school, whether it's someone trying to shovel their driveway of snow? I've seen that one too. Does it matter whether it doesn't matter what they give you. You got to be able to look at a problem. Maybe you get freaked out because there are bananas. I don't know why that freaks you out, but whatever. If you have a banana aversion, I apologize. You won't see bananas this year. I doubt it because they just did them last year. Maybe it'll be apples. Anyway, the BC kids they're gonna have a contest. And they're gonna try and guess what like scenario will be, and they're just gonna like guess all these different types, and it's gonna be like right before the AP. I'll tell you all the things they come up with. Well, what might show up? But long story short. Long story short. Come back. Look at this forever card. Whatever problem you look at, this forever card might apply. And probably will apply on an FRQ. Because what are the two big ideas three big ideas of calculus? Limits, which lead up to derivatives, and ultimately integration. So any word problem you have, is there going to be a derivative or some sort of approximating a derivative probably involved? Yeah, maybe they'll give you an equation of rate. Okay, fine, the derivative is in the rate problem, but still, the derivative is somehow going to be involved, and then the integral is somehow going to be involved, okay? So we can't freak out whenever we see a situation where it's like, oh no, they live in Thomasville, Oregon. People are turning. Anyway, we just have to be able to think of it and say, okay, let's peel away all the extra, and let's just look at the math behind it. Does that make sense? Okay. And what I'm talking about is this little asterisk right here. This one is super good for motion. That particle on an axis, the runner who's running. This is great for motion. But what about degrees Fahrenheit per hour? What about the pot of tea with the biscuits? What about the concert goers? Does this specifically apply? Position and velocity? No. This applies to everything. This is the general one that says, hey, if you want an amount at B, and they give you something to do with rate, you just need to know where it starts and add the integral with the rate, and you've got it. Yeah, so you guys still in the pot of tea and the biscuits one?
Yeah.
Okay, the pot of tea and the biscuits one. Question, what do they give you in the table?
The initial temperature and...
in the table though, don't they just give you degrees Celsius? They just give you the temp?
Yeah.
Okay, so that's not a rate, right? That would be like a position. That would be like an original. That's not a velocity. Now go down to part D though. What do they give you for biscuits?
An initial temperature and a rate that models the decrease in temperature.
Oh, well, they give you B.
Okay, this one's also weird. Do they give you rates?
Yeah, well, they give functions.
Okay, they give functions, but they don't give rates, right? So far, this problem doesn't really seem to apply to this integration as net change idea.
Oh, yeah.
Go find me one of the FRQs that does apply. There's still important stuff with the integral and what it means. And
Isn't it just the 100 plus the integral? Because this will work,
but
right?
we don't want to integrate the rate.
Isn't it? That's fine.
Oh, we do need to integrate the rate for this, but we don't want to integrate B.
Just do 6. Do 6 on the 10.
We'll come back to the pot of tea in a second.
Would 6 be okay?
Which one?
6.
Yeah, look at number 6. Hold on, pause. Is that a rate or is that just a quantity?
That's a quantity.
Ooh, that's a quantity.
Wouldn't
Can you look at the next one though?
7.
Look at the amusement park one.
That's the way people entering it.
Okay, do you see how sometimes they give you a rate and sometimes they give you an original? Okay, so in number 7, they say the rate. I want you guys to all underline the word rate. Super important that you know because, guys, there's no prime on that E or on that L. E is the rate of and L is the rate of. It's the derivative of something, right? The rate. So if they want us to go to people from people per hour, what are we going to have to do? Integrate. So that E and that L, if they want us to go to people from people per hour, we're going to have to integrate. Does that make sense? That is a rate, that is a how fast. If they want us, or if they are asking for anything to do with the number of people, not the how fast, we have to integrate. Now go back to your pot of tea and your biscuits. This one, if they want a temperature, do we need to integrate?
No.
No, because they give us the degrees, right? We don't need to integrate. So then why on earth, if you look at letter B, why is there an integral all of a sudden? It's the integral of the degrees Celsius. Well, wait a minute. What's backwards from the original? What's backwards from position?
Standing still.
In physics, foot-pounds might kind of help at this point, but yeah, but the units, foot-pounds. If you were to integrate temperature, it would actually be temperature times time. It'd be temperature times hour, or degrees Celsius, degrees Celsius minutes. But a lot of you are like, what are degrees Celsius minutes? That's awkward. Guys, do you see how that integral has a 1 over 10 in front? Is there a formula for 1 over b minus a times the integral from a to b of a function? What forever card is that? 1 over b minus a, the integral from a to b of a function.
Average value.
Average value. Guess what that integral is? It's finding the average temperature. Like, wait, but there's an integral. Yeah, but there's also a 1 over 10. This is an average temperature. And so this one's a little weird, but go look at letter C. Now what are you integrating?
H prime.
Ooh. So even though they didn't give you h prime, you're integrating h prime. Well, how can you integrate h prime? Well, we'll talk about that in a second, but what does it mean? Isn't that a part of it? Explain. What's the integral of h prime? What's the integral of any rate? A change. Now, if they don't give us an initial, we're not finding the final. They just gave us the integral and said to interpret it, right? So it's going to be the change in, what's h measured in?
Celsius.
Yeah. So it's going to be the change in temperature in degrees Celsius of my pot of tea. Another way of saying it, I think, is it on the heat or off the heat? The tea. Is it on the burner or has it been taken off the burner? Something's going on. Is it cooling down or heating? It's cooling down. So couldn't we even say better? Hey, that integral says how much the temperature of the tea is going to cool down in the first 10 minutes. That's super practical and someone can understand that. You could also say, oh, well, it's going to be the change in temperature of the pot of tea, from t equals 0 to 10 minutes, which is fine, but it's also a lot more, I don't know, it's a lot easier to understand to just say, hey, it's how much it cools down in the first 10 minutes. Oh, okay. Problem, how are we going to solve for it if they didn't give us h prime?
Values, because they give you your upper bound and your lower bound, so you get 43 minus 66.
Ah, Tyler is saying if we want to solve the definite integral from a to b of the rate, we could just use FTC and say, oh, even though we don't have the rate to actually anti-derive and plug in, do you guys have the original in the table? If I were you on letter C, I would write, oh, it's just going to be h of 10 minus h of 0 using FTC. H is the antiderivative of h prime. So it's just going to be h of 10 minus h of 0, which you can steal from the table up above. So there are many different ways that AP can have you do this. Sometimes you're going to be anti-deriving when you have a rate. Sometimes you're going to be using a table in FTC. But guys, integrals and their meanings are going to show up over and over and over again. Let's go ahead and go in our notes. We peeked at our pocket quite a bit. Now let's do a few examples in our notes just so that we have a feel of what's going on. So in our notes, outside of our packet, remember we have a work day tomorrow and Friday on this worksheet.
Let me see real quick. You told us you want us to work on it. What did you want us to work on? Just start out with number one.
Yeah, see if you can just like maybe start one long answer and one multiple choice. Come in tomorrow. Because you guys will have me. Grade 6 won't have you, but most of them are also gone. I'm leaving at lunchtime tomorrow. And I do have a quick little department meeting today, but that's okay because we're gonna have a work day on this. You guys shouldn't really need to ask me any questions. I'm gonna be kind of unavailable except for Thursday this week. Guys, what do you read this problem? A car moving with an initial velocity. Okay, so can't I name my S of 0 equal to 5? Is that okay?
Yes.
Cool. Accelerates, at the rate of A equals 2.4 miles per hour per second, awkward, for 8 seconds.
Yeah, well, it'd be decent, yeah.
Well, yeah, but position.
Good question. I just read initial and I was being silly. Initial velocity, V of 0 equals 5. Thank you. That was very important. Letter A says, how fast? What are we trying to find, guys? A position, a velocity, or acceleration? Good. Find a velocity. How fast is the car going when the 8 seconds are up? So velocity at 8. How am I going to find it?
We're going to have to integrate A to B up to the car.
Integral gets us change.
Yeah.
So we could go from the beginning to 8 of 2.4 TBT.
And then your initial 5 plus the
It didn't start from 0, it started from 5. Does that make sense? So I need to take my initial, how fast it was going to begin with, and then I need to add my change. Initial amount plus the change, and the change is found from the integral. It's going to equal my final velocity. Ooh, I don't have a table, I don't have a graph, I don't have anything, so I just need to use my math.
1.2 times 8 squared.
So I have 2.4 t squared all over 2 from 0 to 8. Careful, that's separate from the 5 plus. That's separate from the 5 plus. So 5 plus 1.2, 8 squared minus 0 squared. If you guys notice, I just took my little constant out, put in the f of b minus f of a. And I end up with, thanks, Charlotte. Just to model for you, because you guys are going to see a lot of FRQs, I'm just going to go ahead and.
Would that be how they write it? Or would they,
If it's a long answer, that's how you should write it.
but
In the final.
choice, would they do that?
No, you have to simplify multiple choice.
So just help that then.
Yeah, multiple choice, they rarely leave it unsimplified. They never leave it unsimplified with numbers. They sometimes leave it unsimplified as far as like an antiderivative, something like that. Alright, you guys okay? Part B, how far did the car travel during those 8 seconds? How far? What are they asking for?
Asking for position.
Position, change in position, change in distance. How far? So I'm
Just
going
the
to do,
initial position 0, so you just integrate your A of t, yeah, and change in position should be out.
okay. So if we wanted to say what our V of t is, because don't we know that we can find the total distance traveled by integrating velocity? We need our velocity function, which we actually just found. Our velocity function was 1.2 t squared plus, we never did the plus c because we didn't need to, we were just subtracting. But the plus c is also plus our initial velocity, which is why I'm going to make that 1.2 t squared plus 5. And if I needed to find a total distance traveled, I can go from 0 to 8. Yeah. I'm just going to do a dot, 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 because kiddos, I'm more worried about you reading and interpreting and knowing how to start than I necessarily am with you not making any mistakes ever on how to solve. We've been practicing how to solve for a long time. So it's more like how to start. Okay. What about this one? Go ahead and put your pencil down. Don't try to draw this graph. It's going to be too complicated to take too long. But go ahead and check it out. The following is a graph of what?
Velocity.
Velocity. Which means this is time. This is velocity. And then it says initial what? Position. Yeah, initial position. Find where the particle is at the end of the trip. At the end? Well, when does the trip end? At 10. So beginning is at 0, end is at 10, so I need to find the position at 10. What am I going to do? To find the final, I need the initial plus the change. So I can say 2 plus, why am I writing the word area?
You have to find the area under them.
You need to find the area, and the area, and the area. But it's geometry. No wonder they didn't give me a function. I used to say, oh, 1/2 base, 2 times height, 3. Well, 3 times 2 is 6. 6 cut in half is a positive 3. So it just went up 3. Or right 3, right? What's it doing here? Well,
Going backwards.
it's going the other direction, it's going left, and the amount would be, you could do it 2 ways. You could do triangle plus rectangle plus triangle, or you could use your trapezoid. 1/2, I have 1, 2, 3 times 1, 2, 3, 4, 5. Okay, I have base 1 of 3, base 2 of 5. 3 plus 5 is 8. 8 cut in half is 4, and 4 times 3 is 12. Anyway, long story short. When you do the triangles and the rectangle, you should get 12. So it goes to the right 3, to the left 12, and then it goes 1/2 base times height. 3 times 3 is 9. 9 halves. So then say, oh, it's going to equal 2, starting to the right 2 of some reference point, moving to the right 3, moving to the left 12, and then moving back to the right 9 halves.
Hey, where'd you get that? Oh, it's a 2. There we go.
Does that make sense? Why didn't I simplify it? It's a long answer. I'm not simplifying long answers. Part B, what do they want? Isn't the total distance traveled going to equal the integral of the absolute value, and I have 0 to 10? How do I do that? Wait, we just did that, didn't? Oh, what's different?
Reading absolute values.
So isn't it going to be 3 plus 12 plus 9 times? Absolute value says it changes the odometer. It doesn't matter the right and the left, it just matters how far or how much. 3 and 12.
Wait, so why wouldn't we keep the initial position?
Because it's not changing.
Ah.
Oh, okay.
Because they're not asking for where it is, they're just asking for how much the odometer ticked off. So just the change. Does that make sense? Woo! So far I've just been doing motion. What's this one?
1,000 gallons of water.
Gallons! Whatever.
No?
Wait, initially.
Mm-hmm.
So can't I just name that like water? It's up to you. You can name it whatever you want. What if they say V prime? Volume. Oh, volume. Okay. So initial volume is 1,000. I figured out they want V for volume. And then they give us V prime. Drains for 5 minutes. What am I going to do? If they want me to figure out how much does the tank contain after it's been draining for a half hour.
They're going to do the final is equal to 1,000 plus the integral from 0 to the next time.
This in minutes, right?
0 to 5, 30.
I'm trying to find 30
Minus the 30.
because it says half hour, right?
Oh, it does? Oh, yeah, it does.
Okay. Rate of change of its volume after the tank drains for 5 minutes.
So the change, would the change be 0 to 30? 0 to 5?
What they're saying is they kind of were able, after 5 minutes, they were able to determine how the tank was draining. Does that make
To me,
sense?
that sounds like the rate is changing.
So
Which
in
is
some
too
ways, it's an
complicated.
approximate, right?
That's too complicated for us.
So in some ways, it's an approximate. So they're saying it took us 5 minutes to figure out the average flow, and this is it. So that makes sense. Start playing with the worksheet, but we have a work day tomorrow. Juniors, you might want to play with it a little bit more than seniors. I'll see you guys later.
Is your meeting in the class?